First half of this, we're going to go through the embryology of the head and neck development. We're going to look at development of the skull, soft tissue, oral cavity, all the structures of the face and structures of the neck. The second half, we're going to look at clinical issues that may arise from congenital anomalies that result from many different reasons during the development of the head and neck. Have you guys started into the anatomy of head and neck? Have you gotten into that already? Okay, so you're fairly familiar. As you go through this, try to project how the embryology is affecting anatomy. What you know what the endpoint's going to be, so try to project what the embryology is going to present in order to get to that endpoint. And that's especially true when you come to the congenital anomalies. Look at these anomalies and try to estimate what went wrong. What was the actual defect that caused this anomaly? Was it genetic? Was it epigenetic? Was it constraints in the uterus? Was it chemical? Was it, various many reasons. So most of these images you're going to see came from these texts. There's also, we generated a 3D interactive for head and neck embryology several years ago. I think it's still available on the CASE website. Give it a try. Today, why is embryology applicable to head and neck? First, you understand that development helps to define the tissue structure and relationships and enriches your learning of anatomy. So you're able to piece together why this structure is next to another structure. It helps you understand specific cranial nerve distributions and innervations in the function of these cranial nerves. So you're going to go through all the cranial nerves, all the components of the cranial nerves, what exactly are they innervating, what's their role. And also embryology, as we go through today, is going to explain a lot of the congenital anomalies that you might see in your practices as you go through your careers. So when we did heart and lung, we went through this a little bit. Hopefully everybody has some familiarity with early embryogenesis. This is just after gastrulation. This is at about 3 weeks gestation, 3 weeks after fertilization. The embryo is now a disc sitting on top of this empty yolk sac. The yolk sac is depicted here in yellow. It continues on up as a layer called endoderm. That endoderm is going to produce all the lining of the gut. Then in between the next layer, more superficial layer, all this in red here is mesoderm. This mesoderm is going to produce bone, muscle, blood, fascial tissue, things like that. Finally, you have this in blue, the ectoderm. In this case, the ectoderm will form a central nervous system here in the midline. It will also contribute neural crest cells that will form all those structures of the peripheral nervous system. So at this point, this embryo is sitting like a coin sitting on top of a empty bag here in a chicken. Think of a chicken egg. A chicken egg. This yolk sac is filled with yolk. Humans don't use yolk because we have a placenta. So this, like a chicken egg, this would be filled with yolk with the embryo sitting right up on top of that ball of yolk. As development proceeds, the ectoderm starts to go through what's termed neurulation. The mesoderm is instructed that overlying ectoderm to become central nervous system in the midline here. So this structure here is called the notochord. The notochord is sending out signals to that overlying ectoderm telling that you're going to become neural. You're going to become the spinal cord, the brain. So this starts to fold up, goes through folding. This is neural groove formation. The groove will rise up, and pretty soon these two will meet at the midline, and the whole thing will detach and drop away from the surface down into the embryo. At the same time, the mesoderm is going through its specializations. It's subdivided into different regions. There's a axial mesoderm, there's still a notochord down here. Paraxial mesoderm is going to form somites. The somites are going to produce bony structure of the vertebral column. It's going to produce all the skeletal muscle in the body, limbs included. It's also going to produce structures that are important for formation of the dermis region of the epidermis. Finally, you have this endoderm layer here. Eventually, this will fold up into a tube and form the gut tube itself. So here's this large yolk sac with the embryo sitting on top of the yolk sac. At about mid-third week, fourth week, this starts going through what's termed embryonic folding. The brain is growing rapidly. It'll start to push this cranial region forward. This will start to bend over, push what's going to form the heart structures that we've seen before, push it more caudally and ventrally. At the same time, it's pinching off this piece of the endoderm in here that's going to form the foregut. The rest of this is midgut, and the hindgut, there's caudal folding as well that's occurring, doing the same thing, pinching off this portion of endoderm and forming the hindgut as well. So if you look at the head at this point, the cranial region of the embryo at this point is just a massive proliferation of neural ectoderm starting to grow out and starting to, these cells are proliferating rapidly all down through the nervous system. Very quickly, this will start to subdivide in different regional regions of the central nervous system that we'll talk about in a few minutes. Now we're looking at an embryo from above, looking down onto its superior surface. So this is what's termed the neural plate. All of this other structure around is the non-neural ectoderm. It's going to produce all your skin. So this neural plate will begin to go through neural groove formation. This midline will start to drop into the embryo. The two sides will start to build up, and eventually it'll meet at the midline here and form a neural tube. That neural tube is going to form all the structures of the central nervous system: spinal cord, hindbrain, midbrain, forebrain. As these two sides meet laterally here, these cells that are at the transition zone between the tissue that's going to become neural and the remaining non-neural ectoderm here forms cells called neural crust cells. Neural crust cells will separate from both of these structures and begin to migrate out into the embryo. We'll see another slide of this in a few minutes. These neural crust cells are very important. It's going to produce all the structures of the peripheral nervous system. You've talked about it up in the head, the trigeminal ganglion, otic ganglion, all these ganglia up in the head. A lot of them are formed in part from these neural crust cells. Neural crust cells will form part of the adrenal gland and form all the melanocytes in the skin. So neural crust has a very important developmental function, and a lot of people consider these neural crust cells to be a fourth generative layer: ectoderm, endoderm, mesoderm, plus neural crust cells. So we're sitting here just around about 3 weeks. You can see the neural tube begin to fold up, started to fuse. It fuses about mid-embryo level initially. Then it starts to zip up cranially and caudally to form a complete tube, cranial and caudal.
So I'm trying to orient myself right now. The neural crust is above the mesoderm?
So if we translate this into this image over here, neural crest is sitting right in the midline. The neural tube is dropped in. Neural crest is sitting right above where the neural tube is separating from the overlying ectoderm. It will sit there briefly and then start migrating out into the embryo. So it's at the dorsal aspect of the neural tube. And you can see this is happening very quickly. From 20 days to 23 days, this neural tube is zipping up, fusing cranially and caudally. It leaves two openings at either end for a while, an anterior neuropore and a posterior neuropore. Eventually those will close up altogether as well.
Wait, sorry, where do the somites come from?
Somites are from this paraxial mesoderm sitting out in here.
Oh, okay.
So these are mesodermal structures, and what you're seeing in this image are these mesodermal structures with an overlying ectoderm sitting on top of it. So these somites will start to generate all the bony structure of the vertebral column, plus it will provide skeletal muscle and other structures to the embryo.
And so the original, or the first image is a lateral view, and then this is just as if you were looking on top?
This is a cross section for an embryo about mid-embryo. So this is a cross section. This is a sagittal section through an embryo. Here we're looking at a view of the entire embryo from above, and now we're back to a cross section. But it's happening very quick. These neuropores will eventually close up. The act of them closing up takes some time. If they don't close up properly, what will happen is this will stay open. If this stays open, eventually it'll be exposed to this amniotic cavity, the fluid in the amniotic cavity. Over time, that fluid becomes quite caustic because it's made up almost entirely of fetal urine. So this can become quite caustic and start eating away at this brain tissue. So you've heard of anencephaly, a child born without a forebrain. In many cases, it's because this anterior nerve cord never closed and the amniotic fluid ate through the tissue, just destroyed the forebrain. So the defect for that would be that the anterior neural cord didn't close, not that the forebrain didn't form or the amniotic cap or the amniotic fluid was its pH was off or something. It's just that this did not close up entirely. So by the time you finish with embryonic folding, you can see somites here still covered by the ectoderm. These somites are lying deep. You're starting to see limb buds form. We're at about 4 weeks here. Limb bud starts to form. The head is starting to take shape. The cranial portion of the embryo has really gone through a lot of proliferation, so this is very large. It's pushed forward a structure called the frontonasal process here. And you can also start to see these ridges start to form. These are the pharyngeal arches. The pharyngeal arches, during embryogenesis, there's 5 pharyngeal arches that form, 1, 2, 3, 4, and 6. In some species, there's a 5th, there's a number 5 as well. The humans kind of skip over number 5 and go to 6. These pharyngeal arches are going to become very important along with this frontonasal prominence to form structures of the face, to form structures of the neck, thyroid gland, structures of the external ear. We'll get to all those in a few minutes. But you can also see this upper limb forming, the little lower limb bud down here beginning to form. The tail is kind of sweeping around here, kind of lying inside the embryo. So this is another cross section showing the neural tube here, overlying non-neural ectoderm here, neural crest cells forming. The neural crest cells will migrate out. They'll go around somites. This is called a dorsolateral pathway. These cells are destined to become melanocytes in the skin. There's a ventral pathway here. Some of these cells will actually enter the somite, a region of the somite. These cells are destined to become dorsal root ganglion cells, sensory cells of the peripheral nervous system. Other cells will migrate straight ventrally, come to surround notochord and aorta that are laying on either side of the notochord. These will become pre-aortic and para-aortic ganglia that you saw down at abdominal anatomy. These neural crest cells form all along the trunk and the cranial region of the embryo. They all migrate into the embryo. The cranial neural crest cells, the ones that occur from cranial, about the cranial level, the pharyngeal arches start on around. Those are specialized, a little different from the trunk neural crest cells. Cranial neural crest cells can form muscle, they can form bone. Trunk neural crest cells cannot form either one of those structures. So cranial neural crest cells have a little different flavor to them, and they're a little different array of cells and the type of cell types they can differentiate into. These cranial neural crest cells are also the cells that are moved, once they migrate into these bags of ectoderm and endoderm here and begin to fill out, and this is the formation of the pharyngeal arches. We back up just a second. This pharyngeal arch has an outer layer of ectoderm, an inner layer of endoderm because it lines it's lining the gut tube, and in between are neural crests and mesodermal cells that have moved in and kind of ballooned that little packet out. Neural crest cells also migrating into the head are going to be very important in formation of skull structure, of meninges, the dura mater.
Sorry, so cranial neural crest form pharyngeal arches, muscle, and bone?
Cranial neural crest cells will contribute to the pharyngeal arches,
Okay.
but they also are capable of forming muscle and bone.
So then what are the trunk ones?
Trunk neural crest cells will form peripheral nervous system, they'll form melanocytes, they'll form a lot of structures that cranial neural crests can too, but cranial neural crests go on to be able to form bone and muscle at the same time, whereas trunk can't. Neural crest cells don't exist by themselves. They're kind of mixing with mesodermal cells that are derived from mesoderm. The skull has a dual origin. These large flat bones of the skull, I don't know if you talked about intramembranous and intracranial ossification. So these large flat bones are formed almost entirely from intramembranous ossification, whereas the base of the skull is formed from endochondral. These large fat bones have a dual origin. The parietal bone, occipital bone, they're predominantly derived from head mesoderm, just mesoderm that's in the region of the head. Frontal bone has a controversial origin, whereas neural crust cells are moving in and forming that bone itself. So neural crust cells moving into the region form this large flat bone that's really indistinguishable from the other bones formed from mesoderm. However, if you look at the meningeal layers lying beneath that bone, the pia mater and arachnoid mater entirely from cranial to caudal is formed from neural crust cells. Dura mater, on the posterior of the skull, this is a mouse skull that's been stained for using a stain that picks up neural crust-derived tissues. You can see that parietal bones here, occipital bone, is unstained. They're derived from mesoderm, whereas this frontal bone, we have a derivation from neural crust cells. What was long considered the dura mater derived entirely from mesoderm, however, the dura mater lying below this frontal bone here may also be derived from neural crust too. So not only does the skull bone structure itself come from neural crust or mesoderm, the dura mater lying below it may come from mesoderm or neural crust as well. However, all the arachnoid, all the pia is derived from neural crust. So if you go into a mouse, if you do an experiment going in and ablate a lot of neural crust cells, you can lose a lot of pial layer and arachnoid layer in the central nervous system, and that will cause functional defects in the central nervous system. Not that the neural tube won't form, but it doesn't have the proper covering to properly seal in the cerebrospinal fluid to allow proper function of the CNS. So here's an embryo, like I said, about 3.5, 4 weeks. We take a section through frontal nasal prominence, through the pharyngeal arches and the neural tube. And look here, we're looking at a cross section through these pharyngeal arches. So this is arch 1, 2, 3, 4, and 6. Arch 1, all the arches themselves are comprised of similar elements. Each has an external ectodermal layer here. Each has an endodermal layer lining the inside of it. Each arch is separated from the next arch by an external groove and an internal pouch here. Each arch has a cartilaginous component, a neural component, and a vascular component. So each arch has a pharyngeal aorta that's associated, or artery that's associated with it. Each one has some cartilaginous component associated with it, and each one has a cranial nerve that's associated with it. So arch 1, the cranial nerve associated with arch 1 is trigeminal. So if you think about everything that's innervated by trigeminal in the face, all of that is derived from the first arch. Arch 2, its cranial nerve is the facial nerve. So anything you can imagine that's innervated by facial nerve is derived from arch 2, pharyngeal arch 2. Arch 3 is glossopharyngeal, arch 4 and arch 6 are vagus. So each arch has a specific cranial nerve. All the derivatives of that arch are innervated by that cranial nerve. If we look at the arch cartilages, the first arch cartilage is called Meckel's cartilage. Meckel's cartilage has kind of an array. It's laid down very similar to what you would see in the mandible. However, it doesn't contribute to mandible formation. Mandible from the chin all the way back to the coronoid process and to the joint, the temporomandibular joint. Most of it is formed by intramembranous ossification that's ossifying close to Meckel's cartilage, but it's not using Meckel's cartilage to ossify. As you get up to the temporomandibular joint, the joint itself, the structures of the coronoid process, the structures of the joint itself are derived from endochondral ossification that is actually using the end of Meckel's cartilage here to ossify. Two other structures, the malleus and the incus of the middle ear, are also derived from endochondral ossification from that first arch cartilage. So first arch cartilage, the cartilage is associated with the first pharyngeal arch. it kind of is laid down in a pattern of the mandible, but really only a portion of it goes through endochondral ossification to produce bony structure. The rest of it degrades. Where it's degrading, some people think that this is actually leaving a pathway there for the infravelar nerve to innervate all the structures of the mandible. But that's just the hypothesis. The second arch cartilage is called Reichert's cartilage in some texts. It will contribute to the stabies here in the middle ear. The styloid process comes from Reichert's cartilage. Stylohyoid ligament here. The rest of the cartilage kind of degrades. It will also contribute to the lesser horn of the hyoid bone. Fourth arch cartilage contributes to the greater horn and the body of the hyoid bone. Third arch cartilage. Fourth arch cartilage, almost entirely the thyroid cartilage, and really comes down to the cricoid cartilage. Sixth arch may contribute somewhat to the cricoid cartilage, but most of it actually is coming from fourth arch. So most of the cartilaginous structures that are formed from these pharyngeal arches stay as cartilaginous structures. Here are converted to ligamentous structures or disappear entirely. Those that are left behind are listed here. But most of the structure disappears. The grooves and the pouches of each pharyngeal arch becomes very important in formation of specific structures. The first groove here, the groove between arch 1 and arch 2, actually forms the external auditory meatus. This is forming the pathway toward the tympanic membrane. The tympanic membrane is what's left of this junction between endoderm and ectoderm, between arch 1 and arch 2. The first pouch here becomes the tympanic cavity. It's connected to the nasal cavity through the eustachian tube, through the auditory tube. So the groove and the pouch between the first and second arch contribute very much to ear structure. And that's going to be joined, we'll see in a little while, joined by what's termed the otic placoid to form the emery. The rest of the grooves disappear by overgrowth of arch 2. Arch 2 will start to grow down, cover up all the grooves in the rest of the neck, and all those grooves will disappear. This is like when you look at a fish or any kind of animal that uses gills, those arches remain intact, remain open from external to the endoderm. But in humans and in other species, this second arch will start to close up all those structures. Sometimes a little bit of ectoderm is left behind, is caught in here. This can form cyst structures in the neck, and we'll see some examples of those as we go forward. So the only groove of significance that remains is this groove between arch 1 and arch 2, the first pharyngeal groove. The pouches, on the other hand, all the pouches contribute to specific structures. Like I said, the first pouch forms the tympanic cavity. Second pouch is what's termed the tonsillar crypt. This is where the tonsils will form in the posterior of the oral cavity. The pouch itself isn't forming the tonsillar structure. That's lymphoid tissue that migrates into the region. It's just forming the crypt that will house that palatine tonsil. The third pouch will contribute cells of the inferior parathyroid gland that will jump onto the thyroid as the thyroid forms. It will also form the thymus. The thymus forms very early, migrates down to cervical levels, down into the thorax, and sits in the anterior mediastinum. The fourth pouch here will contribute the superior parathyroid glands and another gland called the ultima brachial body that also jumps onto the thyroid gland as it forms. Thyroid forms at the floor between the first and second arch on either side, between the anterior 2/3 of the tongue and the posterior 2/3 of the tongue. There's a little diverticula that forms. It will start to drop down and form the thyroid gland. We'll get to that more in a minute. So these pouches are quite complex. They form a lot of different tissues, and all of those tissues are very important for proper function of the head and neck region. Finally, the aortic arches, each one of the aortic components of each pharyngeal arch will contribute to a normal adult structure. What forms, if the heart is sitting right here, this would be called the aortic sinus. This is that outcrop come from the heart. These are all the aortic arches of each pharyngeal arch coming off. The pharyngeal arches don't form all at once. They're not all present at one time. They form from an anterior to a posterior region. So the first arch forms first, second arch forms, third arch forms. By the time the third arch forms, the first arch is starting to break up into whatever it's going to form. So they're never really all there at one time. So you never really see an image like this where all these aortic arches are in place. By the time you get down to here, all of this is starting to reform into what you would see in an adult. In this little array of aortic arch vasculature, this first arch here will eventually just form part of the maxillary arch, part of the artery that's feeding the face. So have you done maxillary? Have you done infratemporal fossa yet? Okay, so all this maxillary structure is derived from first arch. Stapedial artery is all that's left in the adult. It's all that's left of the second arch. So this little bitty artery in the ear that's feeding structures in the ear is all that's left of the second arch. The third arch is prominent. The third arch will form structures of the common carotid and the internal carotid. So that arch is very important to form those structures that are feeding the head itself. Whereas these other two, the first and second arch, are actually branches that are coming off of the structure. Fourth arch will contribute to the arch of the aorta, and also on the right-hand side will contribute to portions of the subclavian artery. Finally, the sixth arch will form portions of the pulmonary trunk, plus the structures of the ductus arteriosus, this right to left shunt that's there during fetal stages. So all of these pharyngeal arches are remodeled to what you see in the adult or at fetal stages. Some are retained in a large part, for example, arch 3, arch 4. Others will be grayed down to just a very small portion of the vasculature. So this is just a chart showing all the derivatives of each arch. If you look at arch 1, like I said, the trigeminal is the cranial nerve that's associated with arch 1. All the muscles of mastication here, the other muscles in the head that are derived from arch 1 are all innervated by the trigeminal. So this is a way for you to orient, embryology is a way for you to orient the innervation and function of each cranial nerve. And also this chart goes through the grooves and the pouches and what's derived from each one of those. So let's look at a couple of specific arches that are important for head and neck. Arch 1 is going to become very important in formation in the face. Arch 1, very quickly here, you can see this Meckel's cartilage here. Arch 1 very quickly separated into two processes, a maxillary process here and a mandibular process here. These are closely associated with that other large fold that I mentioned a few minutes ago called the frontonasal prominence. And this is almost entirely CNS tissue that's pushed forward. It's still covered with ectoderm, but it's pushed forward and proliferated and becomes this very large structure. So all of this region really is going to become brain. Face hasn't really formed yet. The arches haven't really moved out to form this facial structure.
Is that whole region considered arch 1? Like the maxillary process? And
all of this is arch 1 here. So arch 1 is separated into these two processes, the maxillary and the mandibular.
So that little fold before 1, what's that?
This right here?
Yeah.
That's the maxillary process of arch 1.
Of arch 1. Okay.
Okay. Maxillary process will produce structures of the maxilla. The mandibular process will produce structures of the mandible. So it's not very hard to keep track of. But they are going to both have a tight association with this frontonasal prominence. So if we look at early development, we're looking at 4 weeks here. This is a large frontonasal prominence here. This is the maxillary process of arch 1. This is the mandibular process of arch 1. So we're taking this image and we're looking straight into what's termed the stomadenum. This is the primitive oral cavity. Eventually that will be overgrown by these pharyngeal arches, but we're looking from this direction in this image here. So this would be the stomadeum. The primitive oral cavity is separated from the gut tube by this oral pharyngeal membrane. This membrane will begin to break down in about 4 weeks and open up that gut tube or the proximal end of the gut tube to the amniotic cavity. So once this breaks down, amniotic fluid can move into the stomadeum. Posteriorly, there's another structure called the proctodeum, called the cloacal membrane. That'll break down at about 8 weeks. So after that point, amniotic fluid can be ingested by the embryo, pass through, exit the embryo can add fluid to it as it passes through. This is how the amniotic cavity builds in its body.
That membrane you said opens up the gut tube?
So if you look at this picture, this is the stomadeum, this is the primitive oral cavity. This is going to be eventually made up entirely by ectoderm. Just behind here is an opening into the anterior portion of the gut tube, the endodermal tube that forms. Let me see if I can go back to it. So these are all the pouches. This is all gut tube in here. Let's back up to side. This would be all gut tube. So the oropharyngeal membrane would be sitting right in here. This would be all oral cavity that's going to be formed by these arches. But you can see arch 1 here with the maxillary process and the mandibular process. The mandibular process will come down, meet at the midline, at the ventral midline, and fuse very quickly. So by the time from 4 weeks to 5.5 weeks, the mandible is pretty much fused all the way across. So the mandible forms very quickly. We're going to talk about clefting in the face. It's very rare that a mandible doesn't fuse. There is a mandibular, you can get a mandibular cleft where it doesn't come down and fuse all together, but that's quite rare. This happens very fast, and if it doesn't happen, usually that's other things are associated, and usually that's a lethal situation. This embryo has other things that are wrong with it if the mandibular process doesn't fuse. Maxillary process here never makes it to the ventral midline. It does articulate with the frontal nasal prominence. It has articulates on either side. Also, the frontal nasal prominence starts to produce 2 structures called nasal placodes. These are thickenings of the ectoderm in the frontal nasal process. In the middle of these nasal placodes, the nasal pit forms. It starts to invaginate into the embryo. Those nasal pits are lined by the olfactory epithelium of the cranial nerve 1. So these cells here will eventually form the olfactory epithelium for your sense of smell. However, they dive in and they're forming nasal cavity at the same time. So there's a lot of things happening here at this time. Formation of the nasal cavity, formation of the oral cavity, and the rapid movement and morphogenesis of these pharyngeal arches. This is a lot of material. This is a lot of stuff that's going on. It's very complex. I gave you a PDF that went with this. It's just like heart and lung. Study the PDF, the exam would be just fine. What you really need to do is just sit back and listen so you help you to organize your anatomy. So the mandibular arch here is about 5.5 weeks is fused. You can see these nasal cavities or nasal pits forming. As these nasal pits form, there's two regions here. There's what's called a lateral nasal process and a medial nasal process here, just on either side of that nasal pit. The maxillary process here will articulate with the frontal nasal process on the side, also with the lateral nasal process, and the very tip of it will articulate with the medial nasal process. And it won't move any further toward the ventral midline from that medial nasal process. It will eventually form your entire upper lip, but the middle portion of the upper lip is derived from the frontonasal prominence here in these two nasal processes. So the philtrum, this little divot in your upper lip, is derived from frontonasal prominence, whereas the 2 lateral portions of it come from maxillary processes and move toward the midline. Further development, you can see this maxillary process, everything's kind of coming in and forming properly. You have this articulation with the medial nasal process and lateral nasal process. Here's this philtrum forming, this middle portion of the upper lip. Mandibular process is fused long ago and is normal looking. At the junction between the maxillary process and the second arch, the mandibular process and the second arch, this is the region that's going to form, that groove is going to form the external auditory meatus. Around that groove are going to form what are termed hillocks, auricular hillocks. These auricular hillocks are going to form all the structures of the pinna, the external ear. So all of this structure of my external ear formed at the junction between arch 1 and arch 2. But you can see how low it is on this embryo. It's very cervical. These have to kind of rise up and reposition in order to approach the position where the inner ear is and form a proper ear, but also just to approach a normal location. So you can see this pinna is beginning to form, but it's still real low on the embryo. It still has to rise up with time. At the same time, the eyes are very lateral on this embryo. So the eyes will move in toward the midline, toward the ventral midline as well, at the same time that the ears are rising up. So if you have a child born, full-term child born, their ears are set very low, you need to examine this child that other things are wrong, because the ears are supposed to rise up, and that's a good indication for proper morphogenesis of the head and neck, as well as other structures in the body. If they have the ears that are set real low, you need to examine the limbs, you need to examine the oral cavity, you need to examine the gut, everything on this child to make sure everything is proper. So you can see we're looking at 8 weeks. When is embryogenesis in? When is this guy a fetus? End of 8 weeks, at 9 weeks. So at the end of 8 weeks, the face is pretty much a human face. It looks fairly human. You still have its very large head. A lot of things still have to happen, but everything's kind of apportioned properly. So maxillary process, forming up maxilla, frontonasal prominence, coming down, keeping that maxilla, these plates separate. The mandibular process coming in to form the mandible. So this portion that's derived from the frontonasal prominence, laterally all of this is derived from maxillary process. Here, these are nasal pits, lateral and medial nasal folds here. All of this comes from mandibular process. As this structure comes in, we'll start with the mandibular. As this mandibular process comes in from either side, these two structures have to fuse with each other properly. This is an ectodermal layer, kind of opposing an ectodermal layer. Ectoderm doesn't like ectoderm. It doesn't like to fuse with each other. So as they approach and touch, something has to happen for this structure to fuse properly. What happens is termed a epithelial to mesenchymal transition. The cells that are approaching each other, these ectodermal cells that are approaching each other, as they touch, they transition from an ectodermal orientation and arrangement to a more mesenchymal or mesodermal arrangement. These cells will become migratory. They'll start to move away. And so what's coming up as the seal, this ectodermal fusion, eventually will disappear altogether just into a mesodermal layer. So that will make sure that those two tissues do not separate back out. They'll fuse, and it'll become functional as a single tissue. That occurs here between the maxillary process. So this is the nasal pit. Here's a lateral nasal process, medial nasal process. Here's the maxillary process coming in. It's got to fuse with that medial nasal process here. This is all derived from frontonasal prominence. So at this point, this maxillary process and this medial nasal process come and fuse. The cells at that position move from an ectodermal or an epidermal arrangement to a mesodermal arrangement, and this seam disappears. What happens if that doesn't occur? You can get a cleft formation at that location. There's approximately 16 clefting planes in the face that can occur.
So if it does not bleed, that needs to.
If it does not fuse properly and go through this transition, it can separate back out and form a cleft. Or if it doesn't approach each other properly and never touch, it can form a cleft. Clefting is very, very common. The maxillary process, coming into the midline and fusing, we're looking, what we've done here is we've taken the mandible off the embryo and we're looking straight up at the hard palate. So this is the hard palate forming. The hard palate forms from a portion from frontal nasal prominence, called the primary palate, and two shelves from the maxillary process, called the secondary palate. These two palatal shells move toward each other, toward the midline, and eventually fuse and zip up and form this hard palate. But it's got to fuse with each other, these two shells fuse with each other, but it's also got to fuse properly with that frontal nasal, this primary palate. The primary palate will produce the two midline incisors and whatever those teeth are called on either side. I don't know what those are. What are those? Lateral incisors. So primary, or midline, and lateral. So this hard palate will produce those. The secondary palate will produce all the other structure, all the other teeth. So all these fusion events have to occur properly for the hard palate to form properly. What is also going on at the same time is the tongue is forming. We'll get to tongue in a few minutes. When tongue forms, it's initially lying in between those two palatal shelves that want to approach each other and fuse. You can imagine if the tongue doesn't get out of the way, those two palatal shells can't fuse and you get a clefted palate. What happens though is as the oral cavity expands, the tongue is growing pretty large pretty fast, but then the oral cavity expands very quickly, so the tongue becomes relatively smaller compared to the oral cavity, and it gets out of the way of those palatal shells. But the palatal shells initially are forming in a horizontal orientation as the tongue is sitting in the midline. Once it gets large enough that the tongue moves out of the way, these palatal shells move from a vertical orientation to kind of pop up to a horizontal orientation and then approach each other and fuse. That mechanism from moving to a vertical shelf to a horizontal shelf is unknown. Nobody really knows why it does that, and it does it very, very quickly. So these vertical palatine shells from the maxillary process on either side grow out. They move to horizontal, they move toward the midline and fuse. They fuse with the primary palate, and they're also fusing with the nasal septum in the midline to create a proper hard palate. So just up to now, we've gone through many different morphogenic movements that require many different molecular pathways to get proper signaling and proper orientation to these tissues. Any one of those could have a defect or associated defect and cause a congenital anomaly in these individuals. This is just a slide showing this epithelial to mesenchymal transition, where the epithelia of the palate, here you can see they've fused. You still have a seam in the midline. Eventually that seam will disappear altogether. The cells that are forming that seam will migrate away as mesenchymal cells. The nasal pits that form and are forming that olfactory tissue, they've also formed the nasal cavity. The posterior of the nasal cavity here, this is the frontal nasal prominence with these large brain structures that are associated with it. At the posterior of the nasal cavity, there's little diverticulum forms, there's little pouch forms called Rathke's pouch. It eventually will detach from the oral cavity, and it's forming in response to signals coming from the hypothalamus. This Rathke's pouch will begin to envelop a portion of the hypothalamus and form the pituitary gland. So the anterior lobe of the pituitary gland is derived from nasal epithelium, or epithelium from the nasal cavity, whereas the posterior lobe of the pituitary gland is formed from hypothalamic tissue. So the pituitary is a strange organ. It's CNS controlled, but it's enveloped by this nasal epithelium. This anterior lobe is very important for production of components for proper growth of the embryo. So Rathke's pouch is this little embryonic structure that comes out to initiate formation of the pituitary gland. Teeth, I'm sure you've gone through teeth development. The point I want to make here is you go through all these different steps of tooth development, but this initial step of tooth development, you have a thickening of ectoderm that's responding to signals from the underlying mesoderm. As a general rule, mesoderm tells ectoderm what to do. In formation of a hair cell of hair, mesoderm tells structures in the ectoderm to convert into all the structures to produce a hair follicle. The type of hair, though, is species dependent. That's dependent on the ectoderm.
Actually, isn't the ectoderm from where the neurons and the nervous system are derived? But it's not the one directing traffic?
The ectoderm will produce the central nervous system. But if I think of teeth as just an appendage. So any appendage, nails, hair, eyelashes, things like that, generally the mesoderm is telling it to form.
Okay, at some point there's a switch over.
Well, we're not bringing neural's not coming into play here. The neural will invade that region and innervate that region, but it's not controlling the development of that tooth. The control starts with the mesoderm. Ectoderm takes over that control and tells it what type of tooth to form. The mesoderm is telling it to form a tooth. And that's, all in your revealer processes, the location of the teeth are very narrowly controlled in order for teeth to form in the right position, and that control is also from mesoderm. Appendages, hair, I mean, if you look at a feather, I mean, you can do experiments where you take mesoderm and recombine them with different regions of ectoderm to produce different appendages. If I take mesoderm from my belly and combine it with ectoderm from my back, it will develop a back hair. If I take mesoderm from my back and combine it with my belly ectoderm, it'll develop a hair that's consistent with my belly. Same thing with a lot of different other species. The ectoderm controls species and location type. Mesoderm controls what's forming. So it's a complex interaction, but mesoderm here is under control of the whole thing. If mesoderm doesn't give the proper signals, nothing happens. So we're looking at the other derivatives of the first arch, these ear ossicles. The malleus and incus here are derived from Meckel's cartilage, endochondral ossification of Meckel's cartilage from the first arch. You can imagine if the Meckel's cartilage didn't form properly, you may be missing these ear ossicles. What would the result of that be?
Deafness?
There's different types of deafness. There's neural deafness and conductive deafness. Could this person still hear without an incus, malleus and an incus? If I tapped on the side of the head, would they hear? Yes, because your hair cells would be stimulated. They're still functional. But this would be a situation of conductive hearing loss. Nothing's coming from the eardrum toward the middle ear. And so you can bypass this. You can correct that situation to help this person hear. It's a situation of neural deafness where the hair cells themselves are gone. It's a much more complex situation. This is also the tympanic cavity. This is the pouch between arch 1 and arch 2. You can see these ear ossicles growing within this mesoderm. Eventually this pouch will begin to overgrow those ear ossicles. We'll get to this too when we talk about ear. We'll eventually overgrow those ear ossicles and free those ear ossicles from being buried in this mesodermal tissue and allow them to move. So you can see this tympanic cavity swelling out, growing out, producing, encompassing the ear ossicles, freeing them up. They'll also continue down into the mastoid process as the antrum, mastoid antrum. So all of this is derived from the pouch between arch 1 and arch 2. Okay? So we saw earlier that the aortic portion of arch 1 really degrades and becomes just a little portion of the maxillary artery. The nerve, all the structures we just talked about are innervated by trigeminal nerve. The cartilaginous structure, really the only thing that it's going to contribute to is the ear oscillals and part of the coronary process, part of the T and J as well. Arch 2 is also very important in facial development and the development of the head. Arch 2, as we talked about earlier, Arch 2 will overgrow the more caudal grooves and produce a smooth profile of the neck that you see in most species or species that don't have gill structure. Arch 2 is also very important. I don't know what happened. Arch 2 is also very important in formation of all the muscles of facial expression. So Arch 2 will grow down and cover up these grooves. It will also grow up and intervene into this maxillary and mandibular structure of the face. It'll bring muscle cells up into this region. Those muscle cells will drag facial nerve innervation along with it as they migrate. So all the muscles of facial expression in the head are derived from the second arch and are innervated by the facial nerve, the nerve that's innervating the second arch itself. So like I said, it will overgrow these lower components of the grooves. It will also grow, cover superior and interdigitate between the maxillary and the mandibular processes as well. This is just showing the same thing. Here's Arch 2 overgrowing those lower grooves. Like I said, sometimes you can get a ectodermal structure that's trapped in there that can produce cyst structures in the neck. The thyroid, like I said, the thyroid initially forms at the floor of the gut tube between Arch 1 and Arch 2 on either side. A little diverticula forms here. Through that diverticula, it starts to migrate. This thyroid gland begins to migrate caudally. As it's migrating through, it picks up the inferior and superior parathyroid and the supplement brachial body as well as it migrates through. Remember, the thyroid's coming down into cervical regions, but it's starting up in the oral cavity. So it has to move down through all these structures. So it can move down from the, at the transition through the anterior 2/3 of the tongue and the posterior 1/3 of the tongue. It migrates down, it passes the hyoid bone, passes the thyroid cartilage, and comes to lie surrounding this cricoid cartilage down at cervical levels. Anywhere along this pathway that's migrating, you can find aberrant thyroid tissue that's sitting in that pathway. Sometimes the thyroid starts to migrate down and it can't get past the hyoid bone. So you can have a thyroid gland that's forming at that level of the hyoid bone. This is not a problem for really the thyroid gland. It'll still pump out whatever it needs to produce. However, now it's interfering with function of the hyoid. It can interfere with swallowing, speech, all sorts of things with the hyoid. Sometimes it doesn't migrate at all. You can get what's termed a lingual thyroid that sits up here in the tongue. Once again, it really doesn't matter where the thyroid is. It can still function. However, it's sitting in the tongue, it's going to interfere with tongue function. You can have some issues that develop from that. Tongue itself is derived from pharyngeal arches. Arch 1 here and Arch 3 are large contributors to formation of the mucosal tissue of the tongue. So the anterior 2/3 of the tongue are derived from Arch 1. The mucosa is derived from Arch 1. So therefore its innervation is what? Trigeminal. The posterior 1/3 of the tongue is derived from Arch 3. Glossopharyngeal nerve is innervating the mucosa of the tongue in Arch 3. The root of the tongue comes from Arch 4, so it has a vagal innervation. And so the general sensation to those mucosal tissues are derived from those cranial nerves. Taste buds come from the second arch. Taste buds will migrate, well, it's unclear whether they migrate in or the neural components of the second arch migrate in and form taste buds. But the taste buds of the anterior 2/3 of the tongue are all innervated by facial nerve. The taste buds on the posterior 1/3 of the tongue are still contain glossopharyngeal innervation. What about muscle? The intrinsic musculature of the tongue, these are migrating in from occipital somites, from somites just at the base of the skull. They kind of migrate forward and fill out this bag of mucosa here. And they're dragging their innervation with it. So the hypoglossal nerve is dragged from occipital somites all the way to the tongue to supply all the intrinsic musculature of the tongue. So the tongue has a very, very complex origin from different pharyngeal arches, but also from tissues lying outside of the pharyngeal arches. It's just a scaling of a mouse tongue developing. If you look back, there's specific structures. These two lingual swellings and tuberculum impar, all this is derived from arch 1. This hypobrachial eminence from arch 3. If we look at this mouth structure, these two lingual swellings on either side, they're fusing at the midline. This little other base from arch 1, followed by structures coming from arch 3. So this tongue is forming very early, very fast, and it becomes very large quickly relative to the oral cavity. Then the oral cavity gets larger and larger as the tongue gets relatively small. Brain development, like I said, we're covering a lot of material here. Brain development begins with formation of the neural tube. As the neural tube forms completely, the brain almost immediately starts to subdivide, and the spinal cord starts to subdivide into regions. Spinal cord has very obvious segmental elements to it that form. The brain, its segmental elements are less obvious, and they take a little more time to form. So what starts out as a general neural tube here with head folding starts to generate these flexures. There's a cephalic flexure here and a cervical flexure that forms. Eventually this pontine flexure forms as the cerebellum begins to form here. If we're looking at just a coronal section through this neural tube, at a little after 3 weeks, the cranial portion of the neural tube has formed 3 pouches, 3 vesicles. The prosencephalon here, this is eventually going to form forebrain. The mesencephalon form midbrain, and the rhombencephalon here will form hindbrain, followed more caudally by spinal cord itself. By the time you hit about 5 weeks, that prosencephalon is separated to a telencephalon and a diencephalon. Telencephalon will produce all the cortical tissue. Diencephalon is going to produce some cortical tissue, but it's also going to produce the eye fields, the structures that are going to form eyes. Mesencephalon stays as mesencephalon. The rhombencephalon will eventually form the metacephalon and myelencephalon, different regions of the hindbrain and cerebellum, as that pontine flexure begins to form. Happening very, very quickly. The rhombencephalon here also has a segmental nature that's very similar to what you see in the spinal cord. It's divided into structures called rhombomeres. These rhombomeres, in a human, there's 7 rhombomeres. So it has a segmental nature. Each rhombomere is producing structures that's going to contribute to specific cranial nerves. So cranial nerve 5, trigeminal nerve, is derived from rhombomere 2 and 3. Facial nerve derived from 4 and 5. Glossopharyngeal and vagus derived from 6 and 7, respectively. So these rhombomeres are very important to send out fibers, specific fiber tracts out into the periphery, but that periphery in this case are these pharyngeal arches. Vagus nerve is a little bit different from what you see in other cranial nerves. Vagus nerve, these what are termed vagal crust cells, will migrate out and jump onto the gut tube and then start migrating down the gut tube. I mean, when you went to, good question.
What's the difference between a rhombomere and a pharyngeal arch and a somite?
So a rhombomere is a subdivision of the hindbrain, of the rhombencephalon, this primitive hindbrain. So very early you have this rhombencephalon. It has, just like the spinal cord, it has different spinal segments. The rhombencephalon has different rhombomeres that are segments. The pharyngeal arches are the region of mesoderm, ectoderm, and endoderm that the rhombomere is sending cranial nerves out to. So the rhombomeres will contribute to trigeminal, to facial, to glossopharyngeal, and vagus to innervate those pharyngeal arches. Somites are a little bit more posterior. They're these little balls of mesoderm that's surrounding the spinal canal. It's going to produce bony structure and muscular structure in the trunk of the body. So somites are a little different from anything you see up in the head, although we have these, we back up to tongue, we have these occipital somites. They call them somites, but they're really just masses of mesoderm at the base of the skull that migrate forward to to give you the intrinsic musculature at the top. So all those are very different. Some are mesoderm, some is ectoderm and endoderm, some of it is CNS tissue. Vagus, though, goes through this migration. Vagus will send cells, vagal neural crest, will send cells out to the gut, and those cells will migrate through the gut. And this is going to produce the enteric nervous system of the gut. This is all derived from one region of neural crest up at the, toward the base of the skull. This will be followed by afferent or axons sprouting from the CNS as the vagus that's going to follow these cells as they move down through the gut. And if you follow them, you can see these vagal neural crest cells here, this stippling here, it's kind of moving in. It's followed quickly by neurons that are just right behind this wave of neural crest cells moving down the gut. It'll go all the way, how far down the gut does the vagus innervate? Do you remember? All the way down to the splenic flexure of the large intestine. So the vagus is innervating all the small intestine, all the way around through the cecum, transverse colon, all the way down to the splenic flexure. The rest of it is picked up by sacral parasympathetics, the rest of the gut. So the vagus is really a very, very long nerve in the body. But it's just, all it's doing is following these vagal crest cells down as they populate the gut and form the enteric nervous system. So vagus is very interesting. It's a good model, experimental model to look at neuron migration, glial cell formation, all different types of experiments can occur. So we talked about neural crest, we talked about CNS formation, we talked about pharyngeal arches. Now there's one more aspect of the head that's unique from the trunk, and that's the formation of what's termed placodes. We've already talked about one placode, these nasal placodes that form on the frontal nasal prominence and form the nasal pits and eventually form the olfactory epithelium. But there's other placodes that form. Some form nervous tissue, some form other structures. The otic placode forms all the structures of the inner ear. The lens placode forms the lens of the eye. It has no neural components to it, but has this lens structure that's forming. And that's just thick. These are thickenings of ectoderm that are responding to signals coming from either neural tissue or mesodermal tissue, and they can form different structures. The trigeminal ganglion, I talked a few minutes ago about the trigeminal ganglion is a peripheral ganglion. It's formed from neural crest cells that migrate in, but it's also formed from placodal structure. Different regions of the trigeminal ganglion may come from either placode or neural crest. So placodes are unique to the head, and they're formed from signals coming from underlying structures telling the ectoderm what to do. What's also important is the ectoderm has to know how to respond to those signals. It's termed competence. So the ectoderm has to be competent to respond. A lot of times, especially for like formation of the lens, the lens is formed through the retina telling the overlying ectoderm, you're going to form lens, start to form the placodes. If that tissue can't respond, a lens does not form. So that ectoderm there has to have the proper receptors on its surface to respond to those signals. What tells that tissue to form those receptors is the history that tissue has been through. That tissue has come close, has been received signals from neural tissue. It's received signals from gut tissue through the life of its movements and everything. That tissue has a specific history to tell it eventually you're going to respond to those signals coming from the gut. This is the same as true for all these other placodes. You have what's termed epibrachial placodes. These are placodes that are associated with specific pharyngeal arches and specific cranial nerves. We'll look at a couple of them today. One is the lens placode, and we'll look at Idaho. The other is the otic placode, and that's formed down here adjacent to the rhomencephaline. It's going to form all the structures of the inner ear. All right. Just a couple more minutes. So if we look at the ear itself, remember we talked about the external auditory meatus. This is formed from the groove between arch 1 and arch 2. The pinna, the external ear, as the ear forms, so here's arch 1, arch 2, right in this region, these hillocks, these swellings begin to form here, and those swellings will remodel and form this external ear. all the structures of the external surrounding that external auditory meatus. If you remember, the pouch between arch 1 and arch 2 will form the auditory tube and all the tympanic membrane, all the tympanic cavity. The tympanic membrane itself is formed from the ectoderm, endoderm with an intervening mesodermal layer in between that forms in between arch 1 and arch 2. So external auditory meatus, tympanic membrane, tympanic cavity all form from arch structure. The cochlea, semicircular canals, all the structures of the inner ear are derived from otic placode. So these structures are forming at different locations, and during development of the embryo, they have to come together in order to form a proper ear. The otic placode, so if this is where the external auditory meatus is forming, the otic placode is forming way up here. It starts out as a placode. It's receiving signals from the rhombocephalon saying, you're going to form ear. It forms this placode. The placode begins to dive into the embryo, form this pit, the otic pit. It will detach from the overlying ectoderm as an otic vesicle, very similar to what you saw in the neural tube. It will detach, begin to dive into the embryo, and then go through its morphogenesis to form all the structures of the inner ear. One of the first structures it forms is called the endolymphatic duct. All this tissue can form endolymph. Endolymph is the liquid sitting inside the semicircular canal, sitting inside the cochlea. All this tissue forms endolymph. It will produce endolymph continuously. It has no mechanism to stop forming endolymph. So you can form too much. If you get too much in here and has nowhere to go, this thing will just swell up abnormally. However, you have this endolymphatic duct that will allow drainage of that endolymph back. Here's the endolymphatic duct here. This will connect to the arachnoid layer of the meninges and drain endolymph back into the CSF. There are specific congenital anomalies associated with failure of functioning of that endolymphatic duct. There's specific receptors that can be missing, specific pores that can be missing, so the endolymph can start to swell up. This will swell up the inner ear, the cochlea, the semicircular canals, and start to destroy hair cells and sensory cells within those structures. So you'll have vestibular problems, you'll have balance issues, you have hearing issues, all that just from the overproduction of endolymph in that structure. So the otic placode has become the otic vesicle here. The endolymphatic duct is starting to form. You can see the otic placode begins to morph into two different regions, a saccular region and a utricular region. The utricular region is going to form structures of the semicircular canals, where the saccular portion is going to form structures of the cochlea. So this placode has to go through all these morphogenic movements to produce this structure, but the embryo itself has to go through certain morphogenic movements to bring this structure together with the tympanic cavity, with the external auditory meatus for a functional ear to develop. I think the last thing we're going to cover before we take a break here is the formation of the eye. The eye is formed from outcroppings coming from diencephalon. Those outcroppings coming from diencephalon are going to form all the neural retina of the eye. It's going to form a lot of the iris of the eye, plus the pigmented retina of the eye. But the lens and the cornea are going to be derived from ectodermal structures that are signaled to form in response to the formation of that retina. So very early, if we're looking at an embryo in a cross-section here at the level of diencephalon, these are two, what are termed optic vesicles that are forming. These optic vesicles will approach the overlying ectoderm. As it approaches that ectoderm, they will start to go through this proliferation and form this cup. They'll start to back up from the ectoderm and form this cup structure, the optic vesicle here. As it backs up and forms that cup structure, it's telling that it's also sending signals to that overlying ectoderm to form a lens placode. As the cup deepens, that lens placode forms a lens vesicle and then breaks off just like the otic vesicle did, detaches from the overlying ectoderm, and begin to form a lens structure. So at this point you have this diencephalon-derived structure of the retina and the optic cup. ball sitting in the middle here that's eventually gonna form lens. And then you have this overlying structure that is gonna eventually form cornea in response to the signals coming from the lens. The lens is a very strange structure. It has no neural components to it. The posterior portion of the lens, facing the optic cup, is still receiving signals from that retina. These cells in this region of the lens vesicle will begin to elongate, begin to express crystallines. So this elongation, these cells will begin to elongate and eventually obliterate this cavity completely, whereas these more anterior cells just stay very small, columnar shaped anteriorly. So the lens is an asymmetric structure with its posterior responding to signals from the retina, its anterior providing signals out to this ectoderm here to form cornea. If I took this lens at this point, if I took this lens vesicle out, flipped it around, and put it back in, the cells that were normally here, now sitting on this side, they would start to thicken and lengthen and produce crystallines, whereas these would start to reduce, the crystallines would disappear, and they would start to signal that ectoderm to form cornea. So the lens retains all of its function, no matter what orientation is in. It's just responding to signals coming from retina, and that gives it its orientation. Okay? So we're going to take a break. When we come back, we're going to look at things that can go wrong. So let's take about a 10-minute break here. During embryogenesis, formation of the face, formation of the brain, eyes, ears, things like that. We've gone through a lot of material very fast. And we're looking at all these different morphogenic movements, but the things can go wrong, and things go wrong very, 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 very commonly. Congenital anomalies, and depending on the tissue that's involved, can be extremely common. For example, there's some forms of spina bifida there's estimate of 30% of people have some form of what's called spina bifida occulta. It has no symptoms. It's just a thinning of the lumbar bony structure covering the lumbar central nervous system that can cause some phenotypic, where it's a little tuft of hair at the base of the spine, things like that. It may have no neural symptoms at all. A lot of things can happen during development that can cause these problems. Some of these things are what's termed a failure of specification. An organ or a specific structure doesn't form. It it doesn't even start forming. It never forms. So it's a loss of the structure. Sometimes that's lethal. If portions of the brain don't form properly, it can be a lethal situation. Maybe the gut tube doesn't form properly. It can be a lethal situation. It can be things like where the limbs don't form properly. Not necessarily lethal, but it can be cause extreme issues in the daily living, activities of daily living of that individual. So failure of specification is just a failure of some structure to form. A failure of differentiation may be the structure may try to form, but it forms incorrectly. It forms the wrong type of tissue. It forms the wrong type of cells that are associated with it. Or a failure of proper morphogenesis, it forms everything properly, but it doesn't form the right shape. That can affect things around it as well. So causes of this failure of specification or differentiation of morphogenesis can be chromosomal abnormalities. In a large part, chromosomal abnormalities, loss or duplication of the chromosome, or deletions or additions or all sorts of things in these abnormalities can cause profound effects during development of embryo. Loss of a chromosome in most cases is lethal. There's some chromosomes that you can lose part of the chromosome and survive. Some chromosomes you can get duplication and survive. Most chromosomal duplications are also lethal. So chromosomal abnormalities, especially gross chromosomal abnormalities, in most cases you won't see individuals in the general population with these abnormalities because it was a lethal situation during embryogenesis or fetal stages, or even at the time of birth. If there's a chromosomal abnormality that causes lungs not to form, that child will live all the way full gestation, at birth will die. So there's things like that. So chromosomal abnormalities, epigenetic factors outside of the chromosomes, factors outside of the genome. Uterine constraints is a big one. If the If the uterus is too small, or the amniotic cavity that this child is growing in is too small, it can cause phenotypic abnormalities. It can cause what's called Potter's facies, where the face is kind of smashed in. It can cause limb abnormalities, or you can get syndactyly, or even loss of digits. The other is also true. You can get an amniotic cavity that's way too large. Now the embryo, it can have constraints. That largeness of the cavity can impede on function of the placenta now. So you can have vascular issues, you can have pressure issues, you can have issues that are affecting maternally as well. Secondary effects from extraembryonic defects. So placenta doesn't form properly, it's not attached properly. Maybe the cells have invaded the maternal vasculature too much. You can get what's called preeclampsia. Now you're affecting the mother, which then can affect the child as well. Exposure to teratogens, either biological or chemical. A good one is cocaine. Cocaine or alcohol can cause specific phenotypic issues in development of an embryo or a fetus. Chemicals, a good example is thalidomide. Thalidomide was used years ago to control, not in the United States, in other countries, it was used years ago in the 50s to control nausea during early pregnancy. But it also turns out that it would damage formation of limbs. So you'd have children born without limbs or with partial limbs. So these teratogens or viruses or other chemicals can have profound effects on an embryo. But let's go through some typical ones. In this case, this is called holoprosencephaly. What's happened is the brain, the ventricles of the brain haven't formed, the brain hasn't separated to a kind of a left and right side. It's kind of a global kind of structure. In this case, in a large part, in a very extreme case, the eye fields that are forming from the diencephalon don't separate properly. They stay as one unit. And so in this case, this is a form called cyclopia. This individual, if you look really close, this individual actually has two eyes sitting here. They're just fused in real close. Sometimes that's just one eye, it's just sitting there. What happens here is, since the eye fields couldn't separate, all that structure of the frontonasal prominence couldn't come down to its proper location, so it stayed above the eyes. This is called a proboscis. This is all the structure that was going to form nose, upper lip. It stays up here, so it just does whatever it can at that position. Now you can see the upper lip formed, but it doesn't have a philtrum, it doesn't have all the structure at the upper lip, there's no primary palate in there. So this individual, do you think this is lethal? Do you see people walking around like this? No, but it's not lethal at birth. These individuals can survive for quite a while, but usually they succumb to other problems during early childhood. This individual has the same issue, same diagnosis. His only defect, he has one midline incisor. So he didn't have enough tissue that came down to form a complete primary palate. The primary palate is reduced, and so he has a little, he's good at parties, Other than that, he has no real problems. His eyes are functional. They're a little, you may call those a little bit close together, but they're fully functional. This guy's living a normal life.
That top image, what part of the brain is that? You said that's the brain.
This is all forebrain. You can see forebrain is one sheet. There is no midbrain that's separated into a left and right. It's all stated as a single unit. And this is caused by a defect in mesoderm of the head that's supposed to tell the brain to proliferate and separate to two sides. So that mesoderm is either lacking or not producing enough of the signaling in order to separate these structures into two eye fields. Lissencephaly, smooth brain. In this case, everything internal to the brain, if you cut this brain in half, it looks like a normal brain, except there's no gyri, there's no sulci. So the surface area of the cortex is greatly reduced. So this person has a deficit of not having enough cortical cells. So there's severe cognitive defects, there's severe functional defects, motor defects, not necessarily a lethal situation. These people who are born can live a long time, but they're going to have severe abnormalities, severe defects throughout their life, cognitive and motor. Arrhynia. what's going on here? No nose, no nasal cavity, no olfactory epithelium. What caused this? From what we talked about briefly, what did this person lack? Nasal pits. So the nasal pits never formed. So they never formed a nasal cavity. It's got an oral cavity, but there is no nasal cavity. Can this individual, does he have a sense of smell? No. Can you fix this?
Well,
No. What's it?
well, I was gonna ask if there are olfactory bulbs, or if it's just the, you know, you could make a nose, but if there's no receptor, it doesn't matter.
Exactly. So the olfactory epithelium didn't form. That olfactory epithelium signals the olfactory bulbs to form. So olfactory bulbs would be lost. Cosmetically, you can certainly create a nose for this individual, but they will never have a sense of smell.
Why are the eyes different sizes?
Well, there's other issues going on. This is called macroophthalmia or microophthalmia. He's got other issues there.
Okay.
This is just an example of the same item. But the CNS, would you expect this individual to have cognitive defects, mental retardation, anything like that? There's no reason to suspect that. You have to examine the child further. So congenital abnormalities don't necessarily mean cognitive defects. It can be motor, sensory, all sorts of different things, but you don't have to assume cognitive.
Would they have no sense of taste because they don't have a sense of smell?
Taste buds form without the formation of the nose of olfactory epithelium, but olfactory epithelium enhances taste. So their taste would be different from yours. Craniosynostosis. As the large flat bones in the skull form, they form sutures in between them. That suture is the point of growth of those large flat bones. But they stay separate throughout gestation in order for your brain to grow properly, in order for delivery to be proper, and also postnatal, the brain is really growing fast, so these things are allowing that brain to grow fast. If they fuse, the brain will continue to grow, but it will start deforming the skull in a way. The brain will continue to form, and the skull will respond to that growth. So craniosynostosis, if one of these sutures fuses too quick, the other flat bones have to compensate for that brain growth, and they will grow abnormally. So you can have craniosynostosis that affects any one of these sutures or multiple sutures. If you can have a sagittal suture. Normally a sagittal suture won't fuse until you're in the 60s, 70s, 80s years old, but sometimes it'll fuse during gestation. If it does, the head will deform to accommodate the brain without that sagittal suture. Same thing with coronal sutures, same thing with the occipital sutures back here. Mitopic suture fuses very, very quickly. Birth, the first couple of years, mitopic suture will disappear, but sometimes it fuses very, very early, and you can get problems that form with that. Usually when a suture forms, it will follow what's called Virchow's law. So if you have a prematurely fused suture, the skull growth is restricted in a plane perpendicular to the affected suture and enhanced in a plane parallel to the affected suture. So if I have a early fused sagittal suture, growth will be restricted. Growth will be restricted in this plane, but enhanced in this plane. You understand that? That's a general rule. It doesn't always hold true, especially when you have multiple sutures that are fused.
Does it lead to cognitive development?
It can, but usually that's associated with syndromes that are affecting other things as well. For example, trigonocephaly, the metopic suture fused too early. So now the metopic suture is sitting here. The two frontal bones start out as two bones and fuse into one. Metopic suture is here, so now the head is growing parallel, or displacing parallel to that suture. So you have this large dome that's sitting here. You can go in and correct it, remodel the skull, the brain will respond underneath it, and you can get a good profile. Scaphocephaly, a fused sagittal suture, you can see that you have this large dome here, also the back of the skull. The skull is extended Anterior, posterior. You can do what's called a left core procedure, where you go in, you peel back all the skin, you take the bone, remodel all the bone, you can give a more normal profile to this individual. So in this case, this is strictly cosmetic. It's not doing anything to the CNS. So whatever deficits this child may have had will persist here. But in a lot of cases, there are no deficits. It's just a deformation of the skull.
They don't take out any brain when they do that?
No, you don't take out any brain. You
How
start.
does- how
You
does that
start
work?
slicing away. The brain will deform. As you deform the skull, the brain deforms with it. As long as you're not creating a lot of pressure, as long as you're not decreasing ventricle size, as long as you're not impinging on any vasculature, the brain will accommodate.
If they do that procedure when they're so young, is the skull still able to grow?
Yeah, the skull's still growing quite fast. In this kid, the skull's growing quite fast and the brain's still growing quite fast. So it can
After
accommodate
birth.
all of it. So the further growth, this is planned out where further growth of the skull is growing in a more normal manner.
So do you go through like the bone, or did you go like into like the dura?
You leave the dura intact, you stay on the bony side.
Okay.
You're not messing with the dura.
Uh-huh.
Apert syndrome, this is craniosynostosis is associated with a syndrome. There's a constellation of symptoms. Here you have a fused coronal suture, so now it's growing parallel, so the skull is growing out like this. The incidence of Apert syndrome is about 1 in 60 to 70,000. So is that rare or common? What's the cutoff? Usually about 1 to 2,000 is the cutoff between something that's not so common and something that's rare. So 1 to 60,000 is very, very rare. Usually in a year, there's about 1,000 births at UH, so it would take 70 years to see one of these kids at UH. However, UH Rainbows also serves several million people in the Northeast Ohio, so you see quite a few of these come through UH. So this is very uncommon. It's autosomal dominant, but it's associated with other symptoms such as syndactyly, fused digits. In this case, the digits never separated from each other. The bony structure formed, but the ectoderm stayed intact. It didn't allow separation of the digits. These individuals have severe cognitive deficits. There's other things that are involved here. And usually in these cases, there's very little reason to go in and try to remodel the skull because these individuals aren't living out in the normal world. The cosmetic issues aren't really associated with these.
Can you separate the digits and like with the fingers where?
No, not easily. You can try to make them cosmetically look like fingers, but they won't function properly. You won't have the sensory structure, you won't have all that structure associated. Other things that can go wrong, orbital hypertelorism. Remember I said the eyes start out laterally and they move toward the midline. Sometimes they don't move all the way in, so you have a large space in between here. This is caused by too much frontonasal prominence, too much tissue coming down and keeping these eye fields separated too far. These individuals, this can be corrected somewhat. You can go in and take out, remodel the structure in this case and pull these eyes together. The eye fields or the visual fields of these individuals can be so far apart that they're not overlapping, so they have very difficulty in depth perception. If you take these eyes, you remove the structure, take these eyes and pull them through the midline, you don't really have to do a lot of alignment because eyes are very adjustable. You can take an individual, flip them upside down where they're looking at the world upside down. Within about a week, 10 days, the world looks normal to them again. So your eyes and your CNS pathways that are controlling vision can accommodate very readily. So you can pull these two eye fields in, and over time, there may be astigmatisms, there may be all sorts of stuff associated with it, but over time they can grow and accommodate and be able to see functionally normal. Hypertelorism, you can also have eyes that are too close together. There's not enough, and they have to pull them apart. Chiari malformation. In this case, what's this foramen at the base of the skull called? Foramen magnum. In this case, the foramen magnum may have been too large. So now a portion of cerebellum has protruded or herniated through foramen magnum. Is this a problem?
Yeah.
Why? Why? Oh, hers are. Why is that a problem?
Really, if you move your head, it's gonna like.
Right, it's not supposed to be there. So any movement of the head, just the narrow portion of it, you also have vasculature that's moving up into that region. The vasculature can be impinged. You can have vertebral arteries that are impinged by this structure as it moves through, so you're losing half of your circle of Willis there. So you're very dependent on your carotids to perfuse the brain. So, and also you can damage that cerebellar tissue or damage the spinal cord of that region. So once this is detected, you want to try to correct it. You can correct it by going in, opening up this region, kind of pushing that tissue back up in the skull, and then remodeling that foramen magnum and make it more normal. Now you may have issues. You may have, plates, screws, all sorts of stuff that you may have to fuse some vertebrae to stabilize the region. But you can go in and correct this issue. Hydroencephaly. This is different from hydroencephaly. Hydroencephaly, the shunts of the cerebral spinal fluid are either occluded or they never form. So cerebral spinal fluid is collecting in the skull and expanding the skull. In this case, the skull profile is normal. What's happened is the brain formed normally because that's what the skull profile is depending on, but there was some kind of infarct at one point where the vascular supply was cut off, so all that brain tissue died and was reabsorbed. So this is just a fluid-filled cavity here with some midbrain, hindbrain structures. So would this person have cognitive defects? Severe cognitive defects. Would this person would be on not life support, such as breathing, without the life support, feeding tubes, things like that to keep them alive. Cephalocele, in this case, this is similar. This is a herniation of brain tissue out through a defect in the skull. This is actually not uncommon. This can happen. It's not. Don't want to say it's very common, but it can. It's not unheard of to see this regularly. So this is a herniation of brain tissue out through a defect in the skull. This child was born with this thing protruding out. It may or may not be covered by meningeal layers. If it's covered by meningeal layers, those meningeal layers can partially protect it from the amniotic fluid, so this tissue may be viable. What can you do here?
Smush it back in.
You cannot do that. You cannot smush it back in. All you can really do is protect it for the survival of the child, as long as the child survives. You really can't do much with the child. And what usually happens, there's infarcts, there's bleeding, there's things that can shorten life very quickly. Anencephaly, 1 in 1,000, 1 in 2,500, very common. Over in the anatomy department here, we had a collection of embryos over there. We had 2 of these in that collection. We talked about this earlier. What is this? What can this result from?
Difficulties with intramembranous ossification.
We're before, even earlier than that, closure of that anterior neural pore, closure of the neural tube anteriorly. So the neural tube stayed open, so no cranial cavity could form properly. This stayed open. This tissue was exposed to amniotic fluid. Amniotic fluid degraded it, ate it away. So now this child has no forebrain, or as structures related to forebrain are generally non-functional. What's the survival of this child? Can they be born alive? Certainly. They don't live very long. This child was probably stillborn. This child looks like it was born alive. But failure or closure of the anterior neural bore, cranioschisis, it's a protrusion of the brain outside into the amniotic cavity. The amniotic fluid is degrading the structure. Agnosia. What's the anomaly here? No mandible. Mandibles just never form. So the mandibular process of the first arch never formed. So in this case, you're looking at this individual from below. here, the maxilla formed. Here, you had the palatine shells formed, they tried to fuse, but you still have a cleft sitting here. But look at the ears. The ears remained very low. The ears didn't move up to their proper location. But the pinna, the external ear, formed rather normally. I'm not quite sure this child can't hear. Is this a lethal situation? Would this child be born live? Could they? The child looks fairly normal, just doesn't have a man. So these children can be born live, they can be supported, they can be fed, as long as they're getting fed and as long as their airway is formed properly, these children can live for quite a while. There's no reason to think this person, if they have the proper support, can't live quite a long lifespan.
So can you make a mandible and like do like pathology and?
Can you make a mandible?
I suppose you could 3D print anything, but
Yes.
you still need the TMJ, you still need the gloss.
Cosmetically, you can put a mandible there. Can you make a functional mandible? How would you connect the musculature? How would you do all the mucosa? What would be the interface between that 3D printed or manufactured
Right.
structure and the rest of it? Structurally, cosmetically, you can make a mandible. I mean, prosthetics are very advanced. You can make it where this child looks like they have a mandible, but functionally it wouldn't be useful. So for feeding, they could remove it, eat, put it up. Clefting. Cleft palate. Remember we talked about maxillary process, mandibular process, frontonasal process, the medial and lateral nasal processes. All these come into play to form a normal structures of the face. If any of those, if there's a failure of morphogenesis, a failure of fusion, you can generate clefts. In this case, this individual has a bilateral clefted lip, so the two maxillary processes didn't come in and fuse with that frontonasal properly. Either they didn't approach it, or they approached it, touched it, and then backed away, so it left this cleft. At the same time, it clefted the palate. You can see that the primary palate here is hanging free, so the two palatal shelves of the maxillary process didn't come in the midline and fuse properly. So you have a bilateral clefted lip and a clefted palate. This individual, you can see this primary palate completely separated from the secondary palates. And also the palate, the hard palate itself didn't form. So these are the alveolar processes of the maxilla. This is the primary palate. What can you do here? Can you reconstruct this kid? Yes, yes. You guys go all through the world and do this. So this is construction. You can see this kid's fairly old. I mean, looks a little bit angry, but he's fairly old. So he had the support enough to survive. He was fed enough and had everything he needed to survive, but he needs to correct this in order for his life to approach normal. This is a skull they have in a collection over at Anatomy showing a clefted lip and palate. The bony structure just never formed.
Do you know how common cleft palates are? Cleft lips and cleft palates?
I'm sorry?
How common?
Well, let's see if we got 1 in 500 for clefts. So a clefted lip, a unilateral clefted lip alone is very, very common. Bilateral clefted lip is less common. Bilateral clefted lip with a clefted palate is even less common than that. But 1 in 500, 1 in 2,500, it's a common situation. And in this one, approximately 70% of these clefts, there's no real reason why. Nobody knows why there was a cleft. It was sporadic. In many cases, a lot of different syndromes, clefting is associated with syndrome, but there's a reason why it's there. In most cases here, nobody can explain why clefting happened. This is an example of clefted lip going into the primary palate. Here's a bilateral clefted lip. Here's a clefted secondary palate, and here's the whole thing. Bilateral clefted lip, clefted primary palate, clefted secondary palate. Just examples of the same. Unilateral clefted lip, bilateral. This is called a transverse cleft. This is, the frontonasal prominence comes down, the maxillary process comes in, it's fusing from the corner of the eye all the way down to the medial nasal process. If that fusion doesn't occur properly, you can have a cleft all along that pathway. I think they call it oblique clefts. Oblique clefting. This is quite uncommon, but it happens. General midline clefting, this is a whole different situation. Frontonasal prominence came down, but not sufficiently to create a primary palate, a sufficient primary palate. This is quite rare. This, like I said, clefted mandible, I've never seen one. I've seen a picture of one, but I've never actually seen an actual, the actual event, but it does exist. This is what's called a transverse cleft. This is a cleft between the maxillary process and the mandibular process, all the way back to the external auditory meatus. So this will extend all the way to the ear from the corner of the mouth. Unilateral macrostomia, just a unilateral, overly large oral cavity. This can be bilateral, where the cavity is huge, and you have a transverse cleft going on either side. Can you fix? All of these are fixable, cosmetically and functionally. Here's an example of a transverse cleft from the external auditory meatus all the way through to the oral cavity. Brachial arch anomalies. Brachial arch, pharyngeal arch, same thing. Brachial arch is called brachial arch, usually in higher, or pharyngeal arch in higher species because they have a pharynx, they don't have gill structure. But in this case, these brachial arch anomalies, these are anomalies that can occur from formation of the arch itself or from arch 2 overgrowing structures. So if arch 2 overgrows the other grooves, the lower grooves, but leaves a piece of ectoderm in there, that ectoderm can cause cysts. It can result in cyst structures. But these cyst structures can be extensive. In this case, this is a first arch anomaly. You can have a cyst that's sitting up here around the external auditory meatus, around the parotid gland. It can interfere with facial nerve function. It can interfere with parotid function. What you have to do is you have to go in, open that cyst up, and scrape all that ectodermal tissue out and close it back up. And usually it doesn't recur unless you left some more ectodermal tissue in there. Then it will reform the cyst. In this case, this is the type 1 because it's up by the external auditory meatus. As you move down to the neck, this is the type 2. The cyst can be very strong, very large, and encompass a large portion of the side of the face. Sometimes they can open up to the outside world and start to drain. This is actually, some of these are very common. You see in kids. You can see cyst structures in the neck in kids that are very, very common. Second arch anomalies. These cases, they have types 1 through 4 depending on their orientation around the carotid sheath. If they're very superficial to the carotid sheath, they're type 1. They can be deep to the carotid sheath, down toward the pharynx, that's type 4. So it's just positioning of the cyst. These cysts can extend from the neck, from below the mandible, all the way down to the thoracic cavity. They can be very extensive. So you'd have to open up that entire cyst, take all that tissue out, close it back up, and hope you got it all. But usually they're very small, they're very mild. They show up these little swellings on the side of the kid's neck. You go in, remove the cyst, and it's done. We talked about the thyroid gland and its pathway from the tongue all the way down toward the cricocartilage. That's this normal pathway. We talked about you can find thyroid tissue anywhere along that pathway. If you look at the cadavers, you guys don't dissect, you have prosections, right? In the cadavers, you can get what's called a pyramidal lobe of the thyroid. This is a midline lobe that's kind of pointing up back toward that foramen cecum. In an adult tongue, you have this little blind-ended pouch between the anterior 2/3 and the posterior 1/3 of the tongue mucosa. That blind-ended pouch is the foramen cecum, and that's the remnant for the formation of the thyroid. So the thyroid, you can have cysts that form. If the thyroid leaves tissue along this pathway, you can have cysts that form. In this case is the midline thyroidglossal duct cyst here. Once again, go in and scrape out the tissue, and it's gone. Sometimes the thyroid doesn't migrate. The cells form up in the tongue but don't migrate down toward the cricoid cartilage, and you can form what's termed a lingual thyroid. The thyroids could be functioning normally, but it's going to interfere with the tongue. So you can go in and remove that thyroid and put the individual on supplements to supplement the loss of the thyroid, but the tongue function becomes normal. You can also get into syndromes that can affect different arches. In this case, you have a first arch syndrome called Treacher-Collins. In this case, this is thought to be a defect in the migration and the formation of neural crust cells that fill out the pharyngeal arches. In this case, neural crust cells, not enough neural crust cells migrated in to the first arch, or they migrated in and didn't proliferate properly enough. So you had a loss of tissue, of the bulk tissue that's used to make the face. You have a loss of that tissue, and it results into a loss of bony structure and soft tissue structure. In this case, Treacher-Collins, downslanting eyes and notched lower eyelids can form because the base of the orbit is gone. It's not formed properly. Zygomas may be missing. Mandible can be underdeveloped by absence of cheekbones, so that's a zygoma. Eye socket's gone. Lower jaw is often very small, so the mandible didn't form properly because the mandibular process of the first arch was greatly reduced. Underdeveloped, malformed, or prominent ears. First arch is very important in forming the external ears. So the external ears may be greatly reduced or malpositioned. 1 in 50,000, so it's very rare. Autosomal dominant is passed very readily to progeny. So this is a dad and a son syndrome. You can go in, you can do all sorts of surgeries to correct airway. This can have severe airway problems. You can go in and have surgeries to correct airways. In fact, I think in one of these kids has a tracheostomy. I think it's this one. Has a tracheostomy. So you have to do airway management, management of oral cavities. You may have to correct the orbits a little bit because the orbits are so large, the eyes are unstable. So there's all sorts of surgeries, all sorts of therapies that can be involved to provide these people a more cosmetic appearance, but also a functional aspects of their airway and their swallowing and eating and things like that. Pierre-Robin syndrome is also a first arch syndrome. It has different impact. Usually it's micrognathy is a very small mouth, small jaw. A big one is this glossotosis. This is the tongue has maybe rather than be free to move around, maybe tethered posteriorly. It's kind of pulled back. And that happens very, very early, and that can intervene with the formation of the palate. So the tongue couldn't get out of the way. Those palatal shells couldn't find each other, so now you have a palatal cleft. That palatal cleft can be accompanied by a cleft lip, may or may not be accompanied by a cleft lip. Still 1 in 50,000, very, very rare. Small posteriorized jaw, natal teeth. What's a natal tooth? Born with teeth. This can also be cause a situation called oligodramnose, where you have too little amniotic fluid because all of the oral cavity, everything didn't develop properly early enough to start the amniotic fluid build up early enough, so they can be in a amniotic cavity that's rather small, so it can cause other issues. Beckwith-Wiedemann syndrome, autosomal dominant, is incomplete penetrance, so you may inherit it, but the degree of the syndrome may vary between individuals. Macrosomia, there can be a very large birth rate. Macroglossia, a very large tongue. If the tongue is very large, what can that impinge on?
Breathing.
Well, breathing, eating, but formation of the palate. So if the tongue is very large, it can't get out of the way of those palatal shells. You can also get what's called omphalocele, this herniation of gut tissue into the umbilicus. The normal development of the gut, it normally herniates out into the umbilicus and then retracts back in toward the end of embryogenesis. Sometimes it herniates out and doesn't retract back in, so it stays out in the buildings. You can really just take this stuff, slowly kind of push it back in the amniotic cavity, then correct the defect in the anterior abdominal wall, and the child's fairly normal at that point. The tongue, this large tongue, usually the tongue is protruding, the oral cavity can't accommodate it. In the old days, they used to go in and start hacking away at the tongue to make it smaller. Then they finally realized that if you wait a little while, the oral cavity will increase in size and the tongue can be retracted somewhat back into the oral cavity. You can also do all sorts of manipulations with the mandible to make the oral cavity size a little bit bigger to accommodate the tongue. So rather than going in and hacking at the tongue, it's always better to wait. Crouzon syndrome, 1 in 25,000, still very rare. This is a craniosynostosis that can be associated with any one of these or multiple sutures, but it's also syndromic. You have other syndromes, other symptoms that are associated with it. Hypoplastic midface. The midface is very small and reduced. You can see here everything. If you look at this profile here, the midface is kind of pushed in and small. Exophthalmos. The midface is small. Also the orbital cavity may be small too, so the eyes are kind of protruding out. Mandibular prognathism, mandibles big and protruding. There can also be a hearing loss due to an detritic external auditory canals. So the external auditory canals may not have formed properly, sealed up, and don't exist. So this person is having conductive hearing loss. You can do all sorts of things to transmit that vibration to the cochlea, but the normal transmission through a tympanic membrane, ear ossicles just doesn't exist anymore. This can also happen in this Pierre-Robin syndrome. You can also have hearing abnormalities, and also in trichocolons it can be ear abnormalities. Because you have a maxillary process that's reduced, the ear ossicles may not have developed as they're supposed to. This left foot 3 surgery, once again, it's a facial surgery. You peel back all the soft tissue, reform all the bones, put the soft tissue back up on, and this individual has a more normal profile. Ectrodactyly, ectodermal dysplasia, and clefting. The only reason I have this up here is because you can get, this is a huge syndrome that can affect digits and limbs. You can have what's called a lobster claw situation here, but it also can have a cleft palate. Now the association between formation of digits and cleft palate and formation of the palate, a common mechanism between the two is apoptosis, programmed cell death of tissues. In this case, the programmed cell death was not arranged properly, it was not oriented properly. Same thing could happen here. We have cell death is occurring as this is, that cleft is fusing, as these two structures are fusing. Nager acrofacial dystosis, dysostosis. Here you just have a very small mandible, severe micronopathy, very small mandible. What can you do for this kid?
Put in a trach, apparently.
Put in a trach. These individuals have severe airway issues because this upper portion of the pharynx just didn't form properly. But you can go in and expand the mandible. You can do all sorts of stuff with mandibles. Go in and expand the mandible. The ear's in the normal location. He's probably got other facial issues, but you can expand the mandible, correct the airway, and really improve the quality of life of these individuals. But you can also have other abnormalities that you can't deal with in these individuals. So they have other issues as well. Mobius syndrome. This is a cranial nerve palsy that can affect any of these cranial nerves. And a large part of it may be compression of an artery that's supplying the region of the nuclei of that cranial nerve. So you're getting some CNS destruction because of the artery occlusion, and it can cause these cranial nerve palsies. In this case, this is a facial nerve palsy. Which side is affected?
Left, no, right.
Somebody pinched this kid and started crying. This side of the face isn't responding. So there's a facial nerve palsy on this left side of this individual. What can you do? how much I am. Pendred syndrome or Meniere syndrome. These are examples of what I've talked about, that endolymphatic duct in the otocyst as it, in the otic placoid as it develops. If you have a damage to that endolymphatic duct where it can't exchange endolymph into the CSF and the arachnoid layer of the brain from the otocyst, you can get a swelling of all the tissues that are created by that otic placoid, the semicircular canals and the cochlea. And it can damage all the sensory structures within that. So you're getting a loss of vestibular structures, loss of balance, a loss of hearing, hair cells can be damaged, all sorts of things. Aniridia, what's going on here? No iris. This individual has no iris. Is this lethal? I mean, if I close my eyes, am I lethal? It has no iris. These can be isolated. The only thing wrong with this child, no iris sitting there. Can this person see? Yes. The iris is controlling how much light's coming in. This person can see, but may have to wear sunglasses, really heavy sunglasses that are going into bright lights. So they have no control over the amount of light coming in, but their retina can be functioning just fine. Microphthalmia, the orbit itself is just too small. You can have the opposite, macrophthalmia, where the orbit is too big. In that case, it would protrude out from the bony orbit. Once again, in this case, vision here may have a deficit in vision in that eye because the retina is too small, things aren't aligned, maybe a lens didn't form, things like that. Waardenburg syndrome. One of the symptoms of Waardenburg syndrome is a different coloration in the irises, or different eye color. This is largely due to a failure of formation of pigment of the neural crest cells that are moving into that iris on this side. This is all, Waardenburg syndrome is also accompanied by a tuft of apigmented hair, so silver hair, a little tuft right at the top of the head. It's also accompanied by this difference in eye color from one side to the other. This is a retinopathy that can lead, this is a vascular issue that can lead to retinal ischemia and damage to the retina, detachment of the retina, and blindness. And this can occur during gestational stages prior to birth. And it's a vascular issue, it's a failure of formation, proper formation of the vasculature. Coloboma. As this eye cup forms during development of the eye, it doesn't form as a complete like saucer cut. It has it kind of forms a round vasculature called this hyaline artery. This hyaline artery is eventually going to become the central artery of the retina. It's going to feed all the structure of the retina. As this optic cup is formed, so it forms around that hyaline artery and encompasses it into the optic nerve and into the retina itself. Sometimes, and then it comes down and fuses down here at the base. Sometimes it doesn't fuse, it can leave a little space. That space can lead to a deficit in formation of the iris, deficit in formation of the retina. So that little space, that little cleft in the iris can actually extend back into the retina and cause vision issues. In a lot of cases, it's just sitting out here in the iris. This kid went missing in Portugal several years ago, and they posted this all around they posted this image of her all around the world because she had a very specific coloboma, very specific defect that we used to identify. So this is called coloboma. Coloboma is usually around 6 or 7 o'clock in the iris, but it can occur anywhere around here depending on what is causing the coloboma. Finally, back in your neck of the woods, the what's called hyperdontia. What's the defect here?
It's too good at eating.
What is that?
It's too good at eating.
Too good at eating. So,
Tear it apart.
Can you extract all those? How do you name one of these?
well, that's the trick. You just pull them all out. So what's happened here is the alveolar processes that produce teeth, whatever signals are there to produce the teeth, isn't isolated to the alveolar process. The entire oral cavity, the entire palate became an alveolar process. and started to produce all these teeth.
Now, so is this a problem in the bud cap bell stage, or is this before we start to see?
This is a problem way earlier than that, in the
Okay.
induction of teeth, the induction of what's gonna form the teeth. So this is likely to be a mesodermal problem. And it's a mesodermal problem because all the mesoderm in that region is expressing the factors that are important only in what was supposed to be the alveolar process. So the whole palate is not.
So why did they extract the teeth before placing braces and crowns on their teeth?
What's that?
That patient has
This guy?
braces, well, that one has, he got.
I don't know. I don't know. I don't know. It could be that this person couldn't afford all these extractions.
If you're charging somebody per
You know, I
extraction,
have no idea. When my daughter was born, when my daughter was little, she had perfect baby teeth, but all of her other teeth would come in. It looked like this when you looked at it. Actually.
Yeah.
It was just like a mass of teeth, and they had to go down and do all sorts of extractions. I don't know. I mean, this guy's got braces on his first row. They're not really caring about that. I have no idea.
Stupid orthodontist.
That's it.